So, this is going to be a slightly different talk to the previous ones. We're going to be looking at exporting metrics from the application side. Now, last year, we decided to revamp the Prometheus Ruby client to bring it up to the standards of the other clients, and I'm going to talk a bit more about what that means. And it was an interesting project. I hope you find this interesting. First of all, though, hi, my name is Daniel, and I work at GoCarless. We are a payments company based in London. Now, as you probably noticed, I'm not originally from London. I come from Argentina. So if you were wondering, that's the accent. Now, for us at GoCarless, uptime is critical. And that means, among other things, that having good metrics for our apps is critical. And as you probably guessed by the conference name, we use Prometheus for this. Now, we love Prometheus, but we had a pretty big issue trying to use it from Ruby, which is what our main app is written in. Now, as you know, Prometheus will periodically scrape your app asking for metrics. So we have our apps, which in our case, again, are mainly written in Ruby, and are keeping a bunch of counters in there. Prometheus hits you every few seconds, and you respond with something that looks a little bit like this. And for most languages, you just use the appropriate client library, and the story ends there. However, in Ruby land, and also, by the way, in Python land, the story is a little bit trickier, because Ruby and Python have a global interpreter lock, or GIL, which basically doesn't let your app code run in multiple threads at the same time. So our web servers tend to not be multi-threaded. That doesn't parallelize very well. Instead, we tend to use separate processes, right? Processes don't share memory, which ends up solving the same problem that GIL was trying to solve. And everybody can happily run in parallel, ignoring each other. This is, for example, how Unicorn works, which is one of the most common web servers in Ruby. So when Unicorn starts, it will load your app, and it will fork itself into a master orchestrator process and a bunch of worker processes that are actually going to work on them. When a request comes in, Prometheus will pick a worker that is free and will send it the request and then take the response and send it back to the client. Now, this system works great. It scales really well across cores, and it's how I would say the majority of Ruby web applications are running in production. However, for the Prometheus use case, this is a bit of a problem, because now we have separate processes and they don't share memory. Each one of them is going to have its own counters. When Prometheus hits you asking for your numbers, the Unicorn is going to pick a random worker, and that worker is going to report its numbers. But this is never what you want, because this is a partial view of the system, right? What you want is this. You want this aggregation of all of these numbers. But again, these are separate processes, so there's no way for any worker process to see the numbers on the other to add them together. This is by design, and it's generally a very good thing. But for Prometheus, this is a problem. So a huge chunk of Ruby web applications are running prefix servers in production. And the Prometheus Ruby client doesn't really support this cross-process aggregation, which means most people that are running Ruby in production can't use Prometheus. And this included us. So we wanted to do something about it. And it wasn't just us. This has been the case for quite some people for a pretty long time. And in addition to this cross-process thing, the Ruby client was one of the first libraries to be made. It was made very early in the lifetime of the Prometheus project, which means it was made before the community had figured out some best practices around labels, for example, and stuff like that. So it had a bunch of other issues. Now, there were some workarounds out there. GitLab, for example, forked the official client, and they had a multi-process solution that was using Mmaps. However, it wasn't getting merged into the official client, and it also had all of the other problems with best practices, so we didn't want to use this. Discourse had a completely different approach. Discourse has a separate process that is running alongside your app, and then your app pushes metrics to it, and then that will report to Prometheus. But this one also didn't mesh very well with our setup. So mainly, we didn't want to be on a fork. We wanted to be on the official client. So we got in touch with the maintainers. We roughly agreed on a plan of action, and we decided we would pretty much do a rewrite fixing almost all of these issues. But there was one more extra thing to consider. The maintainers of these client apps really, really care about performance. The idea is instrumentation should be free for your app. If you want to increment a counter a lot inside a tight loop, you should be able to do that and not even notice, ideally. And buried in that long discussion in the 2015 ticket, there was a target. Now, I've changed names because I want to focus on the conversation and know who said what. But basically, one of the maintainers said incrementing a counter should take less than a microsecond. And this started an interesting conversation of whether you could even do this in Ruby, with comments like, surely Ruby can't be that slow. And one of my favorites I guess it's a reason people are like writing C extensions, right? So whatever we did to solve this, it had to be fast, and we had an actual target. We wanted to be able to increment counters in less than a microsecond. Finally, there was one more thing that we and the maintainers agreed that we wanted to do. Instead of having metrics classes like this one, where we store the value of the metrics in an instance variable, we wanted to have a separate place to store these numbers. We wanted to have interchangeable stores. So it goes from something like this to something more like that. And the reason for this is that different projects would have different performance needs. Some people will be running on a single thread, a single process, and really care about performance. Some people would have a web app in multiple processes and they're hitting a database over the network, so who cares about microseconds at that point, right? So we wanted to do this, and this was the plan. We were going to support prefix servers. We were going to abstract away the storage of numbers. We were going to follow all of the current best practices, and importantly, we had to be very fast. But the question was, can we even do this within this budget, right? Like according to this exchange, it said it could or couldn't. And the truth is, at the time, I had no idea. I am mostly a Ruby backend engineer for my day job. So my normal intuition for code and its timings is around the milliseconds land, right? I have no idea how long it takes to set a hash in Ruby or what you can do in a microsecond. So we did a bit of experimentation with this, and the answer is a bit long. The short version of whether you can do this or not in a microsecond is both yes and no. So yeah, let's measure this, right? Like if the question is just, can you increment a value in a hash in a microsecond, we can loop a bunch of times, and then we time that, and then we can also time the empty loop to see how much overhead we added by just measuring. We subtract the two, and you can totally do this. You can do it about 12 times in a microsecond, which is awesome. This is well within our budget. However, in our case, it's not that simple. Now, if you remember that GitHub conversation, they were talking about storing numbers in hashes. But why? Why do we use hashes instead of integers? Well, the answer to that is labels, right? In the Ruby client, labels are specified in a hash with the keys and values, which is the interface that makes most sense for Ruby programmers. And we are internally storing numbers in a hash indexed by those hashes. And the problem with that is when you're going into these indexes, into these hashes, indexing by a hash, you're going to be comparing one hash to another in that linked list instead of comparing constants, which is a lot slower. Now, how slow depends on how big the hashes are, which in our case is how many labels do you have in your metric. So for example, if you have 3 labels, this is going to be about 60 times slower, which is pretty terrible for us. Now, according to best practices, most counters should have no labels. So let's measure that. And it turns out we're still under a microsecond, which is awesome. But if you notice, this is pretty close now, right? And we're just incrementing a little hash. In real life, we need to validate these labels. We need to do some processing on them. And we're not even thread safe. You put a mutex around this thing, and now you're in a microsecond and a half, and you blew our target. So turns out, in a particular situation, the second person in this conversation was right. We can't do it in a microsecond, which is kind of sad. But I think it's important to, beyond looking at just that number, looking at the spirit of the target, right? Like, the important thing here is we really care about making this as fast as humanly possible. And this is going to impact a lot of projects in a lot of companies. So it's really worth investing a lot of time in trying to do that. Now, at this point, we have a rough idea of times. We have abstracted our stores so we can exchange them easily. Now we need to actually solve the problem of sharing these numbers across processes. And how do we do that? Well, we experiment a lot. Basically, at this point, we made it really easy for ourselves to try different stores because it was abstracted away. So we just started trying everything we could think of. And I would like to walk you through 4 of these experiments that we did. Now, first up, let's make it really easy for ourselves. Ruby has this unusual data structure called a p-store. Basically, it's a hash backed by a file on disk. So every time you set the hash, the whole thing gets serialized and put into a file. Every time you read the hash, a value, you just read the whole thing from disk and you get the latest value. And this file happens to have a lock around it. So you can actually do this from multiple processes at the same time, and it's fine, and everybody sees the latest data, and it's safe. And if you think about it, this is pretty much exactly what we need, right? We have this global hash that all of the processes can see, everybody has the latest data, and it's amazing. Except that, from a performance point of view, it's pretty slow. So that wasn't going to work. So we had to take a step back, right? And think like, what are we really trying to do here? Well, we want to have a chunk of memory that is shared between different processes. Now, as a complete aside, one of the great reasons about working at Vocales is the amazing people I'm surrounded with. Now, granted, some of those people are trolls, but the trolls sometimes have good ideas, because SQLite was probably not going to be the solution, but he got me thinking, you know what's a great way of having a bunch of memory shared between processes? It's my good friend Redis, of course. Redis is literally a bunch of memory outside your process that all of the processes in your app can read and write very easily, and we all know it's super fast, right? So this also sounds like exactly what we need. And actually, the Prometheus client for PHP uses Redis for the same reason, so that was promising. So I wrote up a little store that we use Redis as a backend, and I fired up the benchmarks, and it's actually slower than dumping the entire hash to disk every time, which is not great. Now this makes sense, right? Like I was very surprised at the beginning, but talking to Redis involves a lot of ceremony and networking and stuff like that, even if it's in localhost. So compared to just writing a tiny file on your disk from your own process, never really stood a chance. Now, this was surprising and disappointing to me, but it was also kind of a relief, because I didn't want to force everyone that wants metrics for the Ruby app to also have to have a separate Redis process. So it's actually kind of good that this didn't work. Finally, I had no choice but to face the elephant in the room. The consensus from pretty much everyone on how to solve this problem was to use memory maps. This is what the Python client library does, and it's what the GitLab fork also does. However, during most of this project, I was trying really hard to avoid them. The main reason being I didn't know how to use them very well, but I had also heard that somebody mentioned that maybe GitLab in the past had had issues with segfaulting, which is a little scary. So I was trying to avoid this. Now, as a super quick introduction to what we're doing a shared memory map file. Basically, you map a file into memory, and you use the shared flag. And if two processes do this, they both end with the same page in memory for the same file, which means that if one process writes to it, the other process can immediately see that new value. And actually, famously, this is one of the fastest ways to do inter-process communication, as I understand it. So I can see why everyone was suggesting this, right? It sounds like a perfect solution. It's only one slight problem. mmap is a syscall. Does anybody here know how to call a syscall from Ruby? You don't. You do it in C. Now, there's this, which has the most hilarious line I've ever seen in official documentation, but it's not particularly useful. And also, let's say you manage to actually call mmap with this. Now you have a chunk of memory that is yours and a pointer to it. Now what? How are you going to read and write that from Ruby, right? So we need some sort of wrapper. We need a gem that is written in C or something similar that is going to help us do this. Unfortunately, there's this, which is maintained by one of the core contributors to Ruby core. And this gentleman called Aaron Patterson also goes by Tenderlove on the internet. And he's normally hacking on the memory management part of Ruby. So he knows what he's doing, and this filled me with confidence. Now, how do we use this gem? Well, you basically make a file, you initialize it to a certain size, say 1 megabyte, and then you init this mmap object. And now you have this m variable that behaves sort of kind of like a byte array. Now, importantly, it is not a Ruby array. The mmap gem is doing a bunch of magic to make it look like one, but you can kind of use it like one. So if you have a bunch of bytes to write, you just set a range in this array and you're done. Now, the tricky bit is turning stuff, the stuff that you want to store into bytes. Is Julius, where's Julius? Oh, that's a shame. Well, I owe that man all of the beers. Now, this is code that Julius wrote in some branch that I shamelessly stole, and I adapted a little bit. Now, basically, first we need to turn our label set into a string, because you can't just dump a hash into a file, right? So we do that. And then to turn that into bytes, we do it like we did in the old days. We take the string, we pad it to either 4 or 8 byte sizes, and then we store the length, then the string itself, and then the value, the float value that we're going to store, right? So we use this pack function that Ruby has to turn that into a bunch of bytes, and then we set the range in the mmap. But this is the clever part. In addition to that, we take a little hash of our own that we keep in memory, and we keep track of where we put the float in the file, which offset we put the float for that particular key. So the next time we need to update that, we just need to find the position and update those 8 bytes. It's super, super quick. Now, this is pretty clever. Like, I would never have come up with this myself, so props to Julius. Now the question is, how fast is this? Well, it's pretty fast, actually. It's about 6 microseconds. So this was looking very promising as a solution, but it has one tiny problem. In addition to having my little benchmark that I used to time these stores, I also had a stress test script that would just basically hammer them to make sure they're safe. It would just do terrible things to these things. It would have super high numbers of metrics with a ridiculous number of different labels, and it would hit them from different threads in different processes, all competing for the same file, just making sure they were safe. And as soon as I ran that script on my mmap store, I got one of these. Now, I don't know about you, but I had never encountered a seg fault in Ruby, or at least no one that was my fault. And so now I'm using this gem that does some magic memory voodoo that I don't fully understand, and I have this seg fault. And this was kind of the reason I was trying to avoid them in the first place, right? Like, this is what I was afraid might happen, and it precisely happened. So this is not great. And given that this gem was written by Tenderlove, and it was being used by me, it was almost certainly not a bug in the gem. I was almost surely using this wrong. But this is a fairly obscure gem. Like, there's not many people mapping from Ruby. There's not much documentation. I didn't find anyone actually using it. So it's kind of hard to figure out what I'm doing wrong here. And I'm not very strong at C, but I still try to read the code. It's a gigantic C file with 2,500 lines of code. And I genuinely had no way of figuring out what the problem was. So yeah, we were here. And what I managed to figure out by random experimentation is that the problem was some code that I had to resize the mmap if that initial 1 megabyte that I gave it wasn't enough. If that could run, then eventually ended up getting the seg fault. So that's great, because we have no idea why that happens, but at least we can reproduce it reliably. So how do we fix it? We obviously try random things until something sticks, right? And it took a while, because I had no idea what I was looking for. But I ended up making the seg fault stop through an elaborate dance of just first closing the file, then reopening it just to resize it, closing it again, then reopening it and mapping it again. I don't know why, but if you did all of those things, the seg fault didn't happen anymore. So if you have a problem, right, you don't understand the problem. You try random stuff until the problem stops happening, but you don't know why it was happening or why it stopped. How confident are you that that's not going to happen again in production in some random server, in some random mission-critical app, right? I was really, really not comfortable with this. And again, this is precisely why I was avoiding memory maps from the beginning. This is what I was afraid of. So it was fast, but I didn't really trust them. Which leads us to our final experiment, right? If you look at this code again, we are opening a file, and we are doing things to a thing that looks like a file, and we do the kind of things that we normally do with files. We just do it in memory because it's a bit faster than files. But what happens if we ditch the memory maps and we just do this to a file, right? From the code perspective, the only difference is instead of setting this range in this thing that pretends to be an array, we just use good old file functions. We seek to a specific place and we write. And so if you're changing the value, it just looks like this. So it's a file, which is, pretty slow. But we're just doing 6 and writing 8 bytes, which is much more efficient than taking the entire hash and serializing it every time, right? And we're also, for example, using separate files for each metric. So if you're in a multi-threaded app for some reason, in addition to having multiple processes, you're not having so much contention among these files. And that's pretty much it. You have no memory maps. There's no C. There's no seg faults. It's nothing fancy. It's just plain old Ruby writing plain old boring files. But it's files, and we all know that those are pretty slow, right? So the question was how slow this was going to be. And the truth is, this completely blew my mind. Like, I did not expect that at all. And if you think about it, it makes sense. We are not f-syncing. We don't care about that data actually staying in the disk. So we're not actually touching the disk. We're just putting it there, and then the kernel figures it out. But it's still surprisingly fast. And if we compare this to memory maps, we have no external dependencies. We have no risky C code. Definitely no seg faults. It's compatible with all editions of Ruby, because the mmap gem, for example, wasn't very happy with JRuby. It's 100% understandable by any Ruby programmer. And this is the most important part, it had nothing that kept me up at night. All of this for just 3 extra microseconds. This was a no-brainer. That's it. We were pretty much done. I mean, we ended up going with disk as our solution because it was fast enough and it had all of these other trade-offs that made it much safer. Now, we do have a separate gem with the mmap store, and I actually have a better way of resizing the file now, which I'm pretty sure is the right way to do it, and I'm pretty sure it doesn't segfault, but I don't trust it. So if you really want those 3 microseconds back, you can use that at your own risk, but we don't particularly recommend it. So we put it somewhere separate just to make that clear. And this is where we're now. We have, after the rewrite, 3 built-in stores that you can choose from. We have basically an unsynchronized hash in case you're doing single-threaded stuff. We have the synchronized hash, which is the default, which is the same thing but with a mutex around it. And we have the file store for multi-process environments. We also have configurable aggregation for what to do with these multiple values. So now that you have multiple processes, you can have a lot of values and you need to combine them. For counters and histograms, this is very easy, you just sum them. But for gauges, this may not make so much sense. So by default, what we're doing with gauges is we're tagging them with the process ID as a label, and then you can get all of them. But you can change that to have the maximum or the minimum or the sum, like whatever makes sense in your use case. We now require declaring your labels up front when you register your metrics, which is what the best practices ask for. We're better aligned with Ruby conventions. Most importantly, we have keyword arguments, which is where the Ruby code is sort of moving towards. And there's a bunch of performance optimization. As part of the profiling the stores, there was a lot of profiling the actual code that was there anyway. So a bunch of things just got faster in the process, mainly histograms. Histograms are a lot faster now. And we have this idea that was in that long 2015 ticket, which is having a benchmark script, so that if you're making your own store, or if you want to see how much the different stores will impact your runtime scenarios, you can tune a few parameters to make it similar to your use case and test it. So that's pretty useful, I think. And that's it. I mean, we had this giant PR with a massive refactor open for a while, and as part of getting this merged, we ended up becoming maintainers of the gem, which was pretty nice. And now this is merged. It's been running in production in GoCarless for almost a year now. We've been doing some little improvements here and there lately, mostly to documentation and making it easier to get started, but we think this is very solid, and we've recently just released the 1.0. So hopefully everyone will trust this and be able to use it. If any of you are a Ruby shop and you had this problem, now you can have Prometheus in Ruby, which is like, yay. And there's a bunch of other things that I want to talk about for the near future. So one issue we have right now, for example, is when you have a counter, the time series doesn't appear until you increment that counter for the first time. And so when you do a rate, then you miss that first update. So we're going to add a method where if you know what your label set is going to look like up front, you can declare those, and you get this time series starting at 0. We have a situation where you need to start with an empty directory for the place wherever you put these files, because otherwise you're going to be reporting the metrics of your previous run. This is very easy for us because we're running containers that don't have persistent file systems, but some people don't have that, and we want to help with that. We also have too many files. If you have a lot of metrics, because we have one separate file per metric per process, you may end up with lots of files, which ends up being problematic sometimes. And we were massively optimizing the path for incrementing counters, but exports, if you have lots of metrics, are a bit slow. Mostly GitLab has been reporting on this, so we want to work on that. But we're also working on some new interesting ideas. So we had this problem, for example, with long-running tasks, where if you do this, which is the obvious thing to do, to count how long you've been working, you're going to have a chart that shows you're not doing anything, and then all of a sudden you did all at once, right? And even if you don't have long-running tasks, basically, if you have a bunch of workers all 100% busy, your chart should look like the one at the bottom, but they will probably look spiky like the ones at the top, depending on what's running when you get scraped. So that's not great. And this actually bit us a little bit when we had an incident that we were trying to figure out what to do with it. So one of our SREs, Lawrence, has made a complementary gem that will allow you to create a custom collector that is keeping time while your tasks are running. Instead of just at the end, it's just during the execution, which gives you that smooth graph at the bottom that I showed earlier. And we were thinking of maybe incorporating this idea into the official client, or maybe an idea that other clients may want to incorporate. So this is something I'd like to discuss with you guys, mostly see what you think. So I encourage you guys to read this blog post that is beautifully obfuscated by the monitor, and get your opinions on it. Now, finally, there were a lot of people that did a lot of amazing work before we even got here, so I want to mention some of you. Now, I will first apologize for anyone I will definitely have missed, or any credit I may misappropriate. I try to do this as accurately as possible. But we have, in no particular order, Jeffrey Utter, who did a bunch of experiments with p-stores and raindrops, and he had a working implementation of abstracted stores. Kevin Lida and Sam Saffron, they did the work for the, I think the GitLab one was Lida, and Sam Saffron did the one for Discourse, which are really interesting takes on these clients. Julian Volz for figuring out that, Julius Volz, sorry, for figuring out how to use mmapps in Ruby, and that amazing code that I stole, which is awesome. And last but not least, Tobias, who shepherded the client for many years, and then guided us quite a bit when we were trying to approach this, figure out what's the best way. So thanks to all of you, and thanks for everyone for listening. I'm not sure if you want to do Q&A or rant for lunch, to be honest, but. Wow, that was super clear.
Have you tried putting those files in SHM file system, or is it perhaps not practical in your application?
I haven't tried SHM. I've tried tempfs, and basically it makes no difference. So because we're not actually touching the disk, an HDD, an SSD, or tempfs have pretty much the same performance because it's not actually hitting anything interesting.
Thanks. This is super interesting, and maybe this is a naive question for people who have worked in Ruby and Python, unlike me. Is there a reason not to treat each of the processes as essentially a separate instance of the application and let Prometheus do the aggregation? Like you just label each one?
Well, one of the problems you have is, so it's very common for big machines to have like 20, 30 unicorn processes, right? And so when you get hit by Prometheus asking for your metrics, one of those at random will get your metrics, will get its metrics. So there are some that won't report on average, like they will report once every 30 scrape intervals, which is definitely not good. And you will get very uneven distributions of them. So it's not ideal. Sorry? Yeah, not the way Unicorn works. So that's why we need to do this.
To add on to that from the Python side, this is a statement, not a question. In some cases, we just don't even know because someone might be using the multiprocessing module or something. And we literally don't know how many there are going to be. So there is no service discovery because someone's just using it. So it potentially works in the Unicorn's case in both languages, but not in the general case of I want to monitor something multiprocess.
I'm concerned about this.
No. So you talked a lot about the benchmarking of the inserts into the library. What about the benchmarks for the marshalling? Because when we were doing our testing of the GitLab fork of the multiprocess library, we were running into issues where it was taking 45 seconds to marshal the metrics because we were reading, I think, 150 megabytes from the mmap files because we were outputting like 40,000 metrics per multiprocess.
Just use fewer metrics. No.
Yeah. Well, that was fix number one.
No. So this is why I mentioned like future work. One of those was slow exports. So my understanding at the time of working on this was like the focus was on incrementing counter performance. I did not. By design, like intentionally, I didn't look into exporting performance, and I would take decisions that if something allows me to increment the counter faster, but the export will suffer, I would take that trade-off. And now I know that for some cases that's not good enough. We're going to have to work on that.
So now you know I don't throw high when I throw far. Anyone else who dares catch a microphone? Is GitLab using now this this fork?
I believe the answer is no, because of what Ben just mentioned. I believe GitLab is still using their fork, and yes?
Yeah, we do, we're live discussing, the GitLab people are watching the stream and are live discussing contributing our C code back.
Cool, we're gonna have C code backup stream. Yeah, so basically what Ben just said is the GitLab people are discussing this right now, and they will end up possibly sending C code, but they have C code for the export part, and we may end up with that upstream. We'll see how that evolves.
Okay, then we have lunch. I think they won't let you in for another 5 minutes.